Hi, the title of today's talk is called Hybrid Sampling Optimization-Based Planning for Agile Jumping Robots on Challenging Terrains. Legged animals such as squirrels have the unique advantage of making jumps to overcome challenging terrains. They are able to traverse terrains with large height differences and wide gaps. To mimic the performance of such agile animals, two major planning paradigms are proposed. The first being a sampling-based motion planning algorithm. It is computationally cheap because it usually only considers the kinematic aspect of the planning problem. However, if dynamic constraints are explicitly imposed, then it will severely compromise the efficiency. The second paradigm is the optimization-based motion planning. It can handle dynamic as well as control constraints. However, it is computationally expensive. To exploit the advantages of both sampling and the optimization-based method, this work proposes a hybrid sampling optimization-based planner. It is able to generate dynamic motions for single-legged jumping robots to traverse challenging terrains. Specifically, we decouple the original problem into sampling-based planning stage and the optimization stage. The sampling stage searches for a kinematic path while the optimization stage solves for the full dynamics. This figure shows the single-leg jumping robot during the stance phase. During the stance phase, the ground reaction force continuously changed the incoming velocity to the outgoing velocity. This single-legged robot is assumed to be a point mass because the leg inertia is negligible compared to that of the base. A motion primitive is used to enable the hybrid planning framework. It is based on the following assumption. The extension of the incoming parabola P in and outgoing parabola P out will intersect at the contact point. These two parabolas are parameterized by the incoming velocity V in and the outgoing velocity V out respectively, and V in and V out also coincide at the contact point. This motion primitive enables us to decouple the sampling stage from the optimization stage. The sampling stage involves a kinodynamic RT planner, which generates a kinematic path as a sequence of parabolas that connects the start to goal. The optimization stage solves a series of trajectory optimization or TO problems to obtain the stance trajectories. This motion primitive enables us to decouple these two stages because the kinematic path from the sampling stage is preserved in the optimization stage. The existence of stance trajectory is determined by the following trajectory optimization problem. The decision variables include the coefficient for the polynomial that parameterizes the ground reaction force alpha, the stance duration t stance, the state at the touchdown moment x touchdown, and the state at the liftoff moment x liftoff. The objective is to minimize the control effort. The constraints include the kinematic reachability constraint, the joint torque limit constraint, and the boundary state constraint, as well as the friction cone constraint. If we randomly sample the V in and V out pair to get a sequence of parabola, then the success rate of solving the TO problem, as shown on the left-hand side, is low. To limit the state space that we sample, we pre-compute an approximation of the reachability map offline and use it online in the sampling-based planner to increase the success rate of solving the TO problem. And if we can increase the success rate, then we can speed up the planning process. The velocity reachability map R of V in is defined as the set of V out such that the V in V out pair has a solution in the TO problem as shown on the left. For example, the velocity reachability map at point 1 is shown as the red polyhedron on the top, and the velocity reachability map at point 2 is shown as the blue polyhedron on the top. Similarly, the reverse reachability map R inverse of V out is defined as the set of V in such as the V in V out pair has a solution. The utilization of the velocity reachability map is referred to as the reachability-informed control sampling. By using this method, we can construct the rapidly exploring random tree algorithm to construct the tree until the goal region has been reached. Once we have reached the goal region, a kinematic path is extracted from the tree. However, the original path may involve many redundant jumps, which is not efficient. In order to reduce the number of redundant jumps and therefore reduce the solve time for the optimization stage, here we introduce a path shortcut subroutine. Suppose we want to connect node I and node J and make a shortcut. We can do this by attempting to solve a small-scale nonlinear program problem. The decision variables include the outgoing velocity at node I, the incoming velocity at node J, and the arrow time tr. The objective is set to a constant to make this problem a feasibility problem. The constraint includes the following. The outgoing velocity at node I should be within the velocity reachability map at node I. The incoming velocity at node J should be within the reverse reachability map at node J. The node I and node J should obey the projectile kinematics. If the small-scale nonlinear program has a solution, then we can make a shortcut from node I to node J and therefore reduce the number of redundant jumps. And by doing this across the whole path, we can obtain a optimized path star. Path star is then provided to the optimization stage to solve for the trajectory optimization problems and obtain a dynamically feasible trajectory. The proposed hybrid planning algorithm is tested on various terrains. In the first terrain, the robot jumps monotonically from the starting point to the goal region. In the second terrain, the proposed hybrid planning algorithm is able to find a strategy to overcome a more challenging terrain where there's large height differences and the robot has to alternate its jumping directions in order to land on the goal region. We then push the limit of the algorithm by asking it to overcome a wide gap, and the algorithm is able to figure out a strategy to make a small jump in order to gain momentum to clear the wide gap. In the fourth terrain, the robot is able to make intermediate jump to redirect its body momentum in order to clear the wide gap to reach the goal region. In this final example, the algorithm is faced with a relatively complex terrain, and it is able to figure out the strategy to redirect its body momentum and clear a very wide gap and reach the goal region. The proposed hybrid sampling optimization-based planning algorithm is compared with other two methods. The first one is a optimization-based planning algorithm, and the second one is a sampling-based planning algorithm. The optimization-based planning algorithm used here is a mixed integer convex program-based approach. It formulates and solves a MICP to figure out the strategy to overcome a challenging terrain. The sampling-based planning algorithm used here is called a quasi-static planning because it is assumed that at each step, the robot will always start from a static pose. This scenario is presented in Figure A, where the terrain is in this shape and the height of the terrain as well as the width of the gap is varied. The solve time performance of these three methods are plotted in Figure B and Figure C. As can be observed from these two figures, the MICP-based method has the longest solve time, and it cannot solve all of the cases. The quasi-static motion planning algorithm is able to find all the solutions when the height is varied. However, it cannot find a solution when the width of the gap is beyond some threshold. In comparison, the proposed hybrid sampling optimization-based planning algorithm is able to find a solution in all of the cases and its solve time is less than the other two methods. The reason that the quasi-static method cannot find a solution once the gap width is beyond some threshold is because it assumes that the robot always starts from a static pose and it cannot reason about momentum. And in comparison, the hybrid approach leverages the benefits of both the optimization-based method as well as the sampling-based method, and it can reason about momentum, and it's able to figure out strategy to make intermediate jumps to overcome large gaps and jump on high platforms. We have also implemented the jumping motion on a single-legged robot hardware platform. This single-legged robot is mounted on a boom system so that the motion is within a plane. The proposed hybrid planning algorithm is able to find a strategy where the robot makes an intermediate jump on the platform on the left-hand side in order to clear the wide gap and reach the goal region on the right-hand side. In summary, the objective of this work is to generate complex dynamic motions for a single-leg jumping robot to traverse challenging terrains. A motion primitive is utilized to decouple the original problem into a sampling stage and a optimization stage. By pre-computing a velocity reachability map offline, we can achieve a path planning with reachability-informed control sampling. The kinematic path goes through a path shortcut subroutine to get rid of the redundant jumps, and the resulting path is given to the optimization stage, where a series of trajectory optimization is performed at each stance phases to obtain a dynamically feasible solution. That is all. Thank you very much for your attention.